Welcome to our Quantum Deep Dive. Today, we're diving into something that is honestly pretty mind-blowing. We're going to talk about a set of equations, over 150 years old, that are somehow the critical toolkit for building the technology of tomorrow. This whole idea comes from a really fascinating essay by Jörg O. Schnappat, and believe me, it's an incredible story about how the past is literally writing the future. So, let's get into it.
So, right off the bat, this seems like a total paradox, right? I mean, how can the physics from the Victorian era, we're talking steam engines, the first telegraphs, how can that possibly provide the fundamental rules for messing with this super weird quantum world of qubits and entanglement? That's the big question we're going to unravel today. And to really get it, we've got to jump in our time machine and head way back. Before the 1860s, the world of physics looked really different. Two of its most powerful forces, electricity and magnetism, well, they were seen as related, sure, but ultimately they were two separate, very mysterious things. So you had electricity over here, the force that could make sparks fly and run some pretty basic motors, and then you had magnetism over there, that strange, invisible force that makes a compass point north. Now, brilliant folks like Michael Faraday had shown there were deep connections. For instance, they knew a changing magnetic field could create an electric current. But a single, clean, mathematical theory that could explain all of it? Nope. That just didn't exist yet. Okay, and this is where the Scottish physicist James Clerk Maxwell walks onto the stage with just a moment of pure genius. He came up with this new idea, something he called the displacement current. The concept it's really profound, but it's also incredibly elegant. He said a changing electric field, even in the total vacuum of empty space, should create a magnetic field, just like a current of moving charges does. This was the one missing piece of the puzzle that nobody else saw. So with that final piece clicked into place, Maxwell managed to unify all the known electrical and magnetic laws into just 4 beautiful equations. Basically, they say, electric charges create electric fields. There are no magnetic monopoles. A changing magnetic field creates an electric field, and here's the kicker. Both electric currents and changing electric fields create magnetic fields. And when you put these 4 simple-sounding rules together, something absolutely incredible happens. The equations predicted something totally wild, that these fields, now linked together, could create waves that travel all on their own. And when Maxwell actually calculated the speed of these waves, just using the basic constants of electricity and magnetism, the number he got was shockingly familiar. It was the exact measured speed of light. This was the ultimate aha moment. Light wasn't some other thing. It was an electromagnetic wave. In one brilliant move, he tied together electricity, magnetism, and optics forever. Now, Maxwell's theory was a massive success. I mean, it described our everyday world almost perfectly. But as the 20th century got going, physicists started poking around at the atomic scale, and some tiny little cracks started to show up in this beautiful classical picture. Yeah, certain experiments they didn't add up. Take the photoelectric effect. Light would hit a piece of metal and knock electrons off, but it depended on the light's color, not how bright it was. If light was just a continuous wave, that made 0 sense. This pushed Max Planck and then Albert Einstein to this really radical idea. What if light energy wasn't a continuous stream? What if it came in tiny, individual packets? They called these packets quanta, and just like that, the quantum revolution was on. So this all led to a new, much deeper theory, quantum electrodynamics, or QED. It says the electromagnetic field is actually made of these quanta, photons, which get exchanged between charged particles. But, and this is the important part, QED didn't just throw Maxwell's equations in the trash. No way. Instead, it showed that they're the large-scale, classical average of a much weirder quantum reality happening underneath. And this brings us right back to our original question. Far from being some dusty old theory, Maxwell's classical equations have become the essential engineering manual for building the quantum future. Why? Because to control the quantum world, you absolutely have to master the classical fields that surround it and poke it. And you won't find a better example than the race to build a quantum computer. You know, the heart of these machines are qubits, these quantum bits that exist in a fragile state of superposition. But the thing is, these states are ridiculously delicate. So, how do you control them with any kind of precision? Well, the answer is, you use exquisitely controlled electromagnetic fields.
The process is basically the same, no matter what your qubit is made of. First, engineers have to design the physical hardware, like a tiny microwave resonator. And they do that using Maxwell's equations. Next, they use those same equations to figure out the exact shape and timing of the electromagnetic pulse they need to send to do something like flip the qubit from a 0 to a 1. Only after all that classical work is done can they actually touch the quantum state itself.
But it really doesn't stop with just computing. Another mind-bending area is quantum sensing. This is where we use the almost paranoid sensitivity of quantum systems to measure the world around us with a precision that's just, it's hard to even wrap your head around.
And the sheer improvement here is staggering. A quantum sensor, like something called an NV center in a diamond, can detect tiny little changes in a magnetic field that are completely invisible to any classical device. And what is it detecting? It's detecting a classical magnetic field whose behavior is still perfectly described by Maxwell's equations. The quantum system is the ridiculously sensitive probe, but Maxwell's theory is describing the very thing it's measuring.
And finally, let's talk about building a quantum internet. This is all about sending quantum information that's encoded in single particles of light, individual photons, through fiber optic cables or even just through the air. And to do that, you have to build the microscopic plumbing to guide these photons where you want them to go.
You know, on a modern photonic chip, it's a whole network of tiny components. You've got waveguides that act like tiny light pipes, beam splitters that route the photons, and resonators that can trap them. Designing every single one of these things comes down to solving Maxwell's equations on a computer to figure out exactly how light is going to behave in these tiny nanoscale structures. You're literally using a 19th century toolkit to engineer the flow of single quantum particles. It's wild.
So when you just step back and look at the whole picture, it's truly remarkable, isn't it? The language that Maxwell invented to describe the invisible fields all around us has become the very same language we use to design and control the quantum realm. It's just a stunning testament to the deep power and universality of what he discovered.
And I think this quote, which we've adapted from Jörg Oeschnipat's essay, just captures it perfectly. Maxwell's equations aren't some relic of the past that we've moved on from. Not at all. They are an active, vital partner in our quest to build the next wave of technology. They're the bridge between the classical world we live in and the quantum world we're just now learning to command.
Which leaves us with one last thing to think about. If Maxwell's 19th century discovery is still fundamentally shaping our world today, what discoveries being made right now, in our time, are going to be the essential toolkit for the innovators of the 22nd century? Thanks so much for joining us on this explainer, which was based on the fantastic work of Jörg Oeschnipat. For a deeper dive, you can check out his website at schnipat.de. Goodbye for now.
Schnepat.de is a private project by Jörg Oeschnipat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.